Okay, we will finish, I think it's just 4 slides from the material that will be on the test next Tuesday, and then move forward. A lot of the beginning slides is stuff I talked about yesterday during lab, so I'm going to go fairly quickly through those and hopefully get to some really new material. So we ended with this slide and then a clicker question. PHYS law. What's the purpose of PHYS law? Why is it important to, for instance, I talked about firefighters when I introduced it. Why is it important to the firefighters? Okay, there were the aspects of breaking the fire hoses. Ashley? Yeah, how much additional pressure you're going to have to add at the truck for the pressure you need at delivery. So the PHYS law is what tells you about how the pressure is going to change due to the friction between the fluid and the walls of a cylindrical tube. And so this R, like I said during lab yesterday, is just a resistance to flow. So I'm going to put flow resistance. And that flow resistance depends on the area squared. So I gave you this clicker question. We're not doing the clicker question again about the flow rate. And we didn't have time for you to discuss with your classmates and do a second iteration. I just told you the answer. So I want to make sure everybody understands why when my dad had a 90% blockage, okay, I didn't necessarily say my dad, but the person was my dad. No, I did say, yeah. So when my dad had 90% blockage, that meant that he only had 1% of the flow that he would have had for the same pressure differences before. So looking at PHYS law, what does Q stand for? Flow rate, right? As was mentioned last class period, previously, Q stood for heat. Heat? No. Heat. Q will be heat in the next chapter, that was the right answer, but it wasn't previously, yeah. Q next semester will be charge, right? So we have to start putting in our mind that we have multiple meanings for the same symbol. Context is important. So when you see flow rate, you need to know it's Q, but you need to know which Q in which equations. So that Q is the flow rate. I did not talk about this letter right here. How many people are 100% confident they know what that is? 1. How many people have a good idea? 1. Okay, well, then I'm not going to put anyone, well, I'll let Ashley, since she's fully confident, and I know she's correct. It's actually eta. How do you get that on your keyboard? I believe it's use the symbol and then H. But that's the Greek letter eta. Boy, I suddenly start doubting myself, but I'm pretty sure. So that's the viscosity. And the units for that viscosity, if we don't have the simple equation, but in the homework you have to use this equation to solve a problem. And it gives you the viscosity for blood at body temperature is, 2.048 times 10 to the minus. I don't remember the whole thing. And then it has the units like newtons times seconds per, I don't remember the unit. I'm really embarrassed, but the standard unit we use is the PHYS, and I'm pretty sure the PHYS is what those are. I should have had it memorized. I don't. But that is eta. Eta is the viscosity. L is the length of the tube. So just using this equation, it depended on the area of the cylinder squared. So if my dad's artery was 90% blocked, that means area 2, if it's 90% blocked, the open part is 10%, is 0.10 area 1. And so if I do Q2 over Q1, All of these other things are going to be the same except for area 2 squared over area 1 squared. Right, because I said assuming the same pressure difference, and of course it's the same length and the same viscosity. So area 2 squared is 0.10 area 1 quantity squared. So that would be the area 1 squareds cancel. It's just 0.1 squared, which is 0.01. 0.01 is 1%. So the flow rate would be only 1%. That's how that logic worked for the clicker question at the very end of class on Monday. So any questions about how we calculate the flow rate difference with the different size opening? No. Then moving on. We talked about laminar flow and turbulent flow. What does the word laminar mean? In layers, that's right. So from flowing in layers to turbulent flow, we have all kinds of crazy things. What makes that happen? Well, I said in class on Monday, if you have too much friction between the liquid and the surface. And so there is a way of trying to calculate when you're going to switch. But as you'll see, it's really non-clear. So we have this thing we call the Reynolds number, and that's N sub R. And there are two different calculations for it. In a circular pipe, that is, we have a fluid of density rho and viscosity eta flying through a cylindrical pipe. In that case, the Reynolds number is 2 times the density times the speed it's flowing times the radius of the pipe divided by the viscosity. And so you get that number. And if you look down at the bottom part, for flow, the very bottom line, for flow in a circular pipe, so that's the top one, laminar flow occurs for Reynolds numbers under 2,000. So if that number is under 2,000, it should be nice, smooth flow. And turbulent for over 4,000. Well, what happens between 2,000 and 4,000? Yeah, could be. 3,000 comes in between. Very, very astute. It could be either way. It's kind of fuzzy. If everything's perfect, it might still be laminar. You have anything that disrupts it, it's going to get turbulent. Now, the next Reynolds number, the one with the prime in it, is for an object going through a fluid. So that would be something like if I drop an iron ball in water as it goes through the water, I can calculate the Reynolds number for that iron ball going through the water. And there it's the density of the fluid again, not the density of the object, times the velocity it's traveling, times L. L here is the length perpendicular to the direction of motion. And then divided by the viscosity of the fluid. So it's a different calculation to get the Reynolds number here, and it has a different meaning. If the Reynolds number is under 10, then we'll have laminar flow. And if it's over 1,000,000, we'll have turbulent flow. A really, really broad range where we're just not so sure. So what's the difference in turbulent flow and laminar flow in things we're concerned about? Well, a big one is drag. That is, if we have a car traveling through the air. If we have laminar flow, the air resistance on that car is going to be different than if we have turbulent flow. If it's laminar flow, then we're going to use Stokes' law, and you notice that the force that is opposing motion is proportional to the speed if you have laminar flow. If you have turbulent flow, it's proportional to the speed squared. So turbulent flow is generally going to have more resistance to flow because as you go faster, it really goes up. And so those are the two laws, the Stokes equation, the drag equation, that are used to calculate that resistance to motion. So if you have a person that's skydiving, which one of these Reynolds numbers would you use to analyze that person? the second one. This one here, because the person is an object going through a fluid, air. So you would use the density for air. L is the cross-sectional length. So if the person's falling through the air, of course you don't have a uniform length, but if you're all spread eagle, you measure, basically from head to toe and say that's going to be roughly the L I'm going to use. So that'd be your height if you're all spread eagle, just falling down. And then divided by eta, the viscosity for which fluid? Certainly not my blood. The air, right. And so you can calculate the Reynolds number as you're falling. And of course, that Reynolds number is increasing as you fall faster. And then you have the upward force, which would be for lower speeds, this, and for higher speeds, this. And you can calculate where the terminal velocity is. That is the speed where the downward force equals the upward force. And somebody might say, well, how do you know which one of these to use? And you say, well, at low speeds, you're going to be a very low Reynolds number. So at low speeds, it's definitely going to be laminar. And so I'll start by checking what speed Stokes' law would give me for a terminal velocity. That's downward force, mg, upward force, 6 pi r. What is r? That's that resistance number we already calculated. Eta v. Calculate that force of gravity, and find what v makes it so you have a net force of 0. Then you go and you put that v into your Reynolds number equation. If that gives you a Reynolds number less than 10, you're done. If it gives you a Reynolds number more than 1 million, then you know I've got to go to the other one. If it's somewhere in between, you're not so sure. Last thing on fluids. This because, well, I love it. When I was a kid, we went camping a lot. And so mom and dad got camping games, and one of they got was a trackball. Really cool. As a 7-year-old, I can't throw a curveball, but this trackball thing, if you don't know what it is, it's kind of like a lame high-lie thing, or not high-lie, lacrosse. Actually, it is kind of like high-lie too. So you have something like this, has a little cage there with a handle on it, and it has tracks here, and then the ball, you catch the ball and it sits here, and then you fling it so the ball goes up and out here. Because of the tracks there's friction, it makes the ball spin. So when you throw it, the ball comes out with a really significant spin like that. And so you throw that ball, and if I throw it so it's going directly at Peter, as it goes through the air, it's not going to hit Peter. It's going to go up and over him. And so, as kids, you're like, this is great. I want to get the ball to Peter, so I'm going to throw it toward the feet of Erica. I throw it toward the feet of Erica, and it curves over to get to Peter. It's totally cool. So I totally loved playing with that as a kid because, it wasn't what you expect. This is what explains it. It's called the Magnus force. If you like watching baseball, you see pitchers. I think they've changed the names of what they call pitches. These days they call a curveball what I grew up calling a sinker ball. I grew up with a curveball. You throw the ball, flicking it like this. So it has a spin like that, and it'll make the ball, if you're a righty, it's going to curve in toward the right-handed batter or curve out away from the left-handed batter. Whereas a sinker ball, you throw it with your fingers coming over the top, so it's spinning like this, and then it will dive down faster than gravity would make it work. Now, a lot of people question if this is real. You guys, you watch like Fox Sports, and they show you the pitch chart, and they show you the path that normally would take and the path it actually took, and you see, wow, there's a lot of deviation. The path they show for normal is the path that you would have calculated, a month and a half ago from our kinematics, just using the downward acceleration due to gravity and calculating the vertical position and horizontal position independently as a function of time. And then the path it actually shows, well, that's what it really did. To me, when I first started to realize there was something significant going on here, just besides the trackball, you can find a video of, I think it's Christy Matheson. I used to know all the old-time baseball players when I was a kid. That's what I read. And they have a picture of him throwing a curveball with 3 stakes in a perfectly straight line, and he throws that curveball so the ball goes like this. And you're like, you can't deny that ball curved, right? Because people used to say, no, the ball doesn't curve. It's just an optical illusion. So here's what's going on. You throw that ball with a spin. So in both of these pictures, the ball is traveling this direction. Now, because of that spin, this is pulling the air up and over. So you have more air going over, less air going under. It's just like when I had the blow dryer with that ping pong ball. The air is not evenly going around it. There's more going over the top because of the spin. And because there's more air going over the top, it turns out that that makes a lower air pressure on the top. Lower air pressure means the air has a smaller downward force, a bigger upward force. So the air in this case is going to lift it up some. So that's the same as with my trackball going straight at Peter. It goes up and over him because the air pressure lifts it up. Now that is not all. The turbulence back here is also a major factor in its path, but it's a harder one to explain. So let's focus on the easy one. This effect can actually be used. They've made boats where they make a rotating cylinder, and you can use that rotating cylinder to propel the boat, which seems completely impossible. But as long as you have some sideways speed, the boat is traveling forward, you have that rotation, you're going to get the pressure difference that you can use to keep propelling the boat. It's totally fun. So we're not going to do any problems with this. It's just something, to know how it works. So like you're watching baseball with your pops and you say, oh yeah, I know how that curveball works. It's, the Magnus force, basically an application of the Bernoulli principle. Your pops and say, wow, my money's probably going to a good place if my kid learned that in school. Right? Right? Okay. That's the end of the material for the first exam. And like I said, I'm not going to ask you why does a curveball curve specifically. I might ask you about the ping pong ball thing or something like that, but not the curveball. That was for your information, for curiosity. Now we're going to talk about thermodynamics. And the first thing, temperature and heat. I talked about temperature and heat yesterday, so let's have you tell me, what is heat? It's a transfer of energy. It's not just energy, it's a transfer process. What is temperature? Average kinetic energy per molecule. Now, I do need to be careful. The temperature is proportional to the average kinetic energy per molecule, and that proportionality changes depending on the material. If it's an ideal gas, it's a very simple relationship. If it's not an ideal gas, it gets more complicated. But temperature is still proportional to the average kinetic energy. It's just for a given state of a given material, that proportionality varies. So they're not the same. And this here, the reason this picture is in our textbook is because instead of drilling a canning, it's drilling a piece of metal, but you have the same principle that led, I think it was Lord Prescott, to the conclusion that heat is simply a form of energy transfer. This one here, you're having work done because of the heating. You're heating it down here. I can change it to red. You're heating it down here, so you have heat going in, and then you have the steam expanding outward. That's work being done on the environment. So it has both of the two energy things. We already talked about measuring temperature. That was pretty much the goal yesterday. But I have some important words. Thermal contact. Thermal, things having to do with heat. Contact means if you have thermal contact, you have the ability to transfer heat. So if I have thermal contact with you, heat can flow from me to you or from you to me. Now we'll learn there are three mechanisms for heat. One of them requires direct physical contact. So if you have direct physical contact, that's a form of thermal contact. But another one would be if there is, for instance, a wind blowing from you to me. That wind could transfer heat from you into the air and then from the air to me. So that's also a form of thermal contact. And then the final form of thermal contact is actually electromagnetic waves. You have the sun is not touching us, and we don't have any breeze from the sun that's hitting us. There is breeze from the sun that's hitting the surface of the atmosphere, but not us. But we still have waves from the sun that reach us, and we have heating due to that. So those are all forms of thermal contact. If there's no thermal contact, you can't have any heat pass between things. Thermal equilibrium means that you have two things in thermal contact and there is no heat flowing. So I have, here's object 1, here's object 2. They are clearly touching each other, hence they have physical contact, which means thermal contact. And if there is no heat flowing, then we're in thermal equilibrium. And we have some laws of thermodynamics. Well, let's start with the Zeroth Law and move up from there. The Zeroth Law is not the first law that was devised for thermodynamics. But it turned out that when they realized they needed this law, it was so fundamental that they put it under the first one that they had derived. So the first law by thermodynamics, the first one discovered, is that energy cannot be created or destroyed. So if I have a fire, we often say, it's producing energy. So yeah, I put my hand in here, it gets hot. It's not producing energy, it's transforming energy from one type to another. When you have a fire, you start with a fuel and an oxidizer. They have their exothermic reaction that releases heat. Where was that energy released as heat initially? It had to be in my fuel and oxidizer somehow, and where it was in the bonds of the fuel and the oxidizer. When you have combustion, you're breaking bonds, forming new bonds that have a lower energy state. And so because you went from higher energy bonds to lower energy bonds, the excess energy was released as heat. And what is that heat going to do? It's going to immediately make things have a higher temperature. So the first law is that you can't create or destroy energy. You can only transform it from one type to another. The second law, one statement of the second law is the one that I was working on here. So first law. Okay, let's do it like this. Laws. Number 1, energy cannot be created or just, come on. And we usually write this as an equation. U is our symbol for the internal energy of an object, the total energy of an object. So if I take this piece of mass, its internal energy is going to be the sum of the kinetic energies of all of the molecules and potential energies of all of the molecules. That's the internal energy. U is our internal energy. And we say delta U, the change in internal energy, is equal to the heat added Heat is adding energy. So if you add, heat is energy flow. So if the heat is added, if the energy is coming in, that's going to raise your internal energy. Minus the work done. Work done is energy going out. That's why it has a minus sign. Now notice I put heat added and work done. Some textbooks put heat added plus work on the system. Work on the system is energy coming in. Work done by the system is going out. And so that's why there's the different signs. So you have to be really aware of the actual meaning so that you can see both writings of the law and understand they're the same thing. It's just one was talking about the work done on the system. So I'm going to actually say done on system to be really clear. And if you have the plus sign, it's the work done by the system. So that's the first law. The second law is that when you have two objects in thermal contact, what does it mean if they're in thermal contact? I heard two answers, but I didn't distinguish what either one said. Not that they have the same temperature. That would be thermal equilibrium. Okay, heat can, not energy, specifically heat, can go between the two, is what thermal contact means. Physically touching is a form of thermal contact, but they're not the only one. It is the one we usually talk about. So if they're in thermal contact, heat can pass between them. Then heat spontaneously or naturally flows from hotter object to colder object. Now, at first, that seems real obvious. Something's hot, something's cold. It goes from the hot, heat goes from the hot to the cold. But sometimes it gets a little confusing because I can have something like this little thing. I can heat it up to 100 degrees Celsius and put it in this water that's at 20 degrees Celsius. There's a lot more of that water than there is of this. So if you calculate the total internal energy, the water has more internal energy than this little mass does. But when I put it in there, energy doesn't flow from the one with higher energy to lower energy. It flows from the one with the higher temperature to the lower temperature. So it will flow out of this, out of the thing with the lower energy with higher temperature, into the thing with the higher energy but lower temperature. So the key is, second law, heat flows from the hotter thing to the colder thing. And now this brings us around to that Zeroth Law. The Zeroth Law is called the Zeroth Law because after they got these first two, they said, whoa, we missed something important. What did they miss? It seems so obvious. I'm going to say it in long words and then write it in a short equation. So I'm only going to write the short equation. The long words, if object A is in thermal equilibrium with object B. Now, what does that mean in equation if object A is in thermal equilibrium with object B? If there's thermal equilibrium, you said no heat transfer. Thermal equilibrium, you put them in thermal contact and there's no heat transfer. Second law, heat always flows from the hotter one to the colder one. So if you put them together and there's no heat flow, what does that tell you? Same temperature. So mathematically, that first statement, if object A is in thermal equilibrium with object B, means if temperature A is equal to temperature B. And if object B is in thermal equilibrium with object C, which mathematically is temperature B equals temperature C, then the end of this is object A will be in thermal equilibrium with object C. Now you can see this here mathematically is just ridiculously simple, which is why no one ever thought that this would be a necessary rule, a necessary law for thermodynamics. But as they studied temperature more carefully and came to a better understanding of temperature, believe it or not, the true definition of temperature is pretty convoluted. They were like, whoa, this was non-obvious. And so they had to come back and define this as a very fundamental law, and that's why they shoved it before the first law, because it's more fundamental than the first law. So there are 3 of the 4 laws of thermodynamics. Let's just go straight to the 4th one so we can say, yeah, we've looked at all of the laws of thermodynamics. The 3rd law is real simple. Nothing can reach absolute zero temperature. Why is that a law? There's a simple explanation for it. Fundamentally, you change the temperature of something by bringing it in thermal contact with something colder. You bring it in thermal contact with something colder, the temperature will drop, right? Because heat, second law, heat spontaneously flows from the hotter thing to the colder thing. So if I want to bring something down to absolute zero, I have to bring in thermal contact with something that has a temperature lower than absolute zero. But absolute zero is called absolute zero because it's impossible to have anything lower than absolute zero. But if you can't have anything lower than absolute zero, you don't have anything to pull the temperature down to absolute zero. Now this begs a little question: how do they get close to absolute zero? Because in research, scientists will take a gas and lower it to temperatures arbitrarily close to absolute zero, like 0.05 microkelvins. Like, how do they get it down to 0.05 microkelvins? Pretty reasonable question, don't you think? They do things like laser cooling. And anyone that knows about lasers says, oh, wait a minute. Lasers are electromagnetic waves. That's radiation, a form of heating. How do you cool it with heat? Well, what you do is you actually create a pocket in electromagnetic waves that constrains the particle and kind of stops it. That's how they cool them as much as they can. So it's kind of like making a trap that holds the molecules to slow them down. So those are your laws of thermodynamics. Zeroth Law: if temperature A equals temperature B and temperature B equals temperature C, then temperature A equals temperature C. First law: energy can't be created or destroyed. Second law: when two things are in thermal contact, energy spontaneously flows from the hotter thing to the colder thing. There are other statements of the second law that we will learn. Another statement of the second law that you may have heard is that in any interaction, the entropy of the universe stays the same or increases. So once we define entropy, that will be another way of stating this. Another one that I like to use for the second law is things naturally try to go to the lowest available potential energy state. You know, if I take the stylus and let go, it falls down. Not gonna do it because I just paid $100 for this thing. If I drop it, it's gonna go to a lower potential energy state because it's available to it. That's an outcome of the second law. In fact, the second law is sometimes called time's arrow, because the second law is the only law in all of physics that tells us the direction things should travel in time. And so it's really important. Without the second law, it would be perfectly acceptable for this thing here to suddenly shoot up off the table and the table to get cold. Right? Because the table cooling means energy left the table. It could go into this and be converted into kinetic energy, and it flies up. There's nothing in physics that says that cannot happen except the second law. Is that a question, Jeffrey, or a stretch? Okay. Now, getting back onto the ordered lecture, I've covered everything on that page. Here's just talking about the second law, heat flowing from the hotter thing to the colder thing, regardless of the sizes or the total internal energies. Temperature scales, we talked about them in lab. 1724 is when Gabriel Fahrenheit came up with his Fahrenheit scale. 1742 is when under Celsius came up with his centigrade scale. And we talked about his original scale had 100 degrees Celsius was the freezing temperature of water and 0 degrees Celsius was the boiling temperature. He died and they turned that upside down. If we look at the boiling temperature of water and the freezing temperature of water, the difference here is 100 degrees Celsius. And the difference on the other side is 180, not 200, 180 degrees Fahrenheit. So a temperature change, now let me show you something. I should have written it like that. Because for temperature change, the convention is to put the degree sign after the unit. So 100 Celsius degrees is equal to 180 Fahrenheit degrees. But 180 degrees or 100 degrees Celsius is not equal to 180 degrees Fahrenheit. Confusing, right? So I'm not going to say silly things on that or expect you to have that all down pat. A temperature change of 100 Celsius degrees is the same as the temperature change of 180 degrees Fahrenheit degrees. So that allows us to make a quick temperature conversion. If I want to go from Fahrenheit to Celsius, I'll take this 0 is equal 32 offset, so temperature Fahrenheit minus 32, and then use the ratio 100 divided by 180. 100 over 180. Well, I will first divide both of these by 10 to get rid of those zeros. 10 over 18 is divide everything by 2 equal to 5 over 9, and that's where that number comes from. So that's how you get the conversion factor. And of course, you can just invert that then. Temperature Fahrenheit is going to be 9/5 temperature Celsius plus that offset of 32 degrees. So changing back and forth is real simple. Physicists love this joke. It's so cold, it's minus 40 degrees. You didn't give units. Is that Celsius or Fahrenheit? And then we laugh because it's so funny. Because you don't have to give the units at that point because they're the same, you know. Unless, of course, well, it couldn't be kelvins. Why couldn't it have been kelvins? You don't say degrees, and it doesn't go negative. Yeah, that's also true. If you have a negative Kelvin temperature, you have something special going on. Now, believe it or not, it is possible to get a negative temperature. A negative temperature is higher than infinite temperature, which means it's dealing with that much more complicated definition of temperature. You can get a negative temperature in very extreme conditions, which clearly we won't talk about. Okay, so everybody understand why physicists think we're so funny? Do you think we're Looney Tunes? No, we have good senses of humor. You know. Okay, temperature scales, absolute zero. Absolute zero is minus 273.15 in Celsius, minus 459.67 in Fahrenheit. Let's suppose that you're from one of those last holdout countries that uses Fahrenheit. If you wanted to have an absolute temperature scale, but you love Fahrenheit, there is a scale for you. It's called the Rankine scale. The Rankine scale is the Fahrenheit temperature plus 459.67. So that 0 degrees Rankine is absolute zero. But nobody ever uses that for a very simple reason. What scale do scientists use? We use Celsius. And since we use Celsius, if we're doing a science problem, we're going to use the Kelvin scale. People who aren't doing science may use the Fahrenheit scale, but since they're not doing science, they're not going to care about absolute temperature. They're never going to use the Rankine scale. Hence, it's just not used. So you don't have to know a thing about the Rankine scale. Forget I ever mentioned it. Got it? Yeah. Normal body temperature, by the way, 37 degrees. Is that what you found in lab yesterday? The reason I had you wait like 15 minutes with it sitting there while I'm talking is so that you would get there, right? Because if you only wait like 5 minutes, it'll be like at 35 or something stupid. Well, something stupid, something wrong like that, right? That's why we waited so long to get it to body temperature. Okay, our first clicker question. I didn't go over this today carefully. 2 correct answers here. So put in your correct answers and click enter. Which statements are true about the Celsius temperature scale? Not yet, Trace. There you go. Okay, Ashley, Christian, Edward, Augusta, Eric, James, Brittany, Brandon, Amanda, and nice. All right, most of them came in. Now it's just Augusta and Brandon. Now it's just Brandon. This is probably the only clicker question we're getting to, so I want to make sure everybody got. Oh, and James. Forgot James. You're going to have to join the ranks of Trace. I want to make sure he gets credit, everybody. I'm sorry about the delay. You're hitting enter, right? Okay, there we go. Okay, answers we had 10, 18, 16, 3, and 12. Okay. Augusta, give us one answer that you thought was correct and defend it. Okay, she said A, it was developed by a Swede. Why do you know this? I don't know. I just do. Well, it's absolutely true. I went and visited Sweden for, I don't know, I think it was the second time. I may not have gone there when I was 2. I don't recall. This summer, randomly ran into a 4th cousin, which is the closest relative I would still have living in Sweden because my great-grandparents came to America. I thought that was totally cool. Okay, so that's why we have the Sweden one there. Next person to answer. Gila, give us another answer. Defend it. You put B? Okay, and why'd you put B? Okay, she said because the other 3 are false. I said there were 2, and she determines the other 3 are false. That is a valid reason. Now, initially, it was the centigrade scale as devised by Anders Celsius. When it was flipped over, it was still a centigrade scale. But 1970s, it got switched to being a 99.99 instead of centigrade. So it's no longer centigrade. Right. The centigrade means that your calibration is 100 degrees between the 2 calibration points. And it no longer has 100 degrees between the 2 calibration points. It's 99.99 between the 2 calibration points. Truth.
That's close enough.
You are no scientist if you say close enough. Originally, okay, so let's go for a third person. Edward. Well, it's not B. Good. Not B. It's not A because A was already correct. E is in exponential. Okay, E is an exponential. Why?
Because scientists use Celsius, not as often as Kelvin, which I think is the actual SI unit.
You are right. The actual answer is Kelvin is the SI unit. But the difference in Celsius degrees is the same as the difference in Kelvin, so we use it a lot.
Yeah, but I didn't agree with the other 2, so I can keep.
Okay, we'll cross that out. Eric.
I remember before you said that they flipped it, so originally 0 was the boiling water.
Yep. Those were the two correct answers. Kelvin is an absolute. Kelvin applies to both this and this. Originally, 0 degrees temperature of boiling water, and that was flipped after he died. So now 0 is temperature of freezing water. Cool things. I'm going to do my demonstrations now, and then it's time to roll. Now, just a little safety thing. I use 1, 2, 3, 4, 5 matches in testing this before class because it turns out, well, I had a hole in the gas line. I blew it out by having it on too hard, all kinds of things. So you got to check these things before class and not just go with it. Here is a Bunsen burner. If you look down the front of it, you see it's got a little wire grid there. What's the point of that? To give it more laminar, super laminar type flow, so it's more uniform. It's exactly right. Now I'm going to take this wand and put it in the fire. What's going to happen? We'll see. Good answer. We'll see. Oh, look at that. It curls up into a nice little circle. And it turns color. It's turning color because it's giving off radiation, one of the 3 forms of heat. When it's hot enough, that radiation gets to the visible spectrum. Why did it curve? It's made out of 2 materials. And when you heat them up, what should happen? They should expand. And so one expanded more than the other. And so if you have 2 things that start the same length and one expands more than the other, it forms a circle, so the longer one's on the outside and the shorter one's on the inside. Now this here is a little more fun, I think. I have a hole, I have a ball, the ball goes through the hole. I'm going to heat up the ball. What's going to happen? It's going to expand. So if it expands, now I have to heat it up. I counted it. It was 20 seconds before class. So let's try to leave it in there at least 20 seconds. If it expands, then it won't go through this hole, right? So let's see. Still does. Needs more time. Gonna take some time. Whole lot of precious time. Gonna take some patience and time to do it right now. That's true. I'm sad to hear that. Okay, now it won't go through. Well, what can I do to make it go through? I could cool it, or I can heat up the ring. Now, if I heat up the ring, what's happening to the metal in the ring? It's expanding. So what's that doing to the hole? Okay, see, I would have said, well, if it's expanding, it's going bigger on the outside and bigger on the inside, so it's getting smaller. But it turns out, I'll tell you now, because, of course, we're out of time and you guys want to leave, that that's wrong. The inside also grows. So when you heat something up, the hole grows. Now, you might think maybe I just shrunk this. So cool it down, no longer fits through. Cool it down, now it fits through. Why did it have the cool sound when I stuck it in the water? Is what? Okay, I had rapid heat transfer to the water, making the water that it was touching instantly boil. And when the water boils, it increases in volume incredibly, and that makes the sound we hear.